So this video is a continuation of the previous video I had on transformers, and in this one we are going through other layers of the transformer architecture. So this is a brief recall of what we discussed the last time. So here are a few different layers of the transformer network. First you have the input, which is in this case cat is an, so we are keeping it simple, just 3 words, and we are considering the next word prediction problem. So this sequence then goes through a tokenization step, which converts this sequence into a sequence of numbers, and now we can use matrix vector multiplication technologies to really predict the next word. Then this goes through an embedding layer, which captures the semantic meaning behind this sentence. And then we combine that with positional encodings, and we take the two encodings, the embedding encoding and the positional encodings, and we plug them into the transformer block, which contains different components. So in the last video we discussed the self-attention component. In this one I'll be discussing something called normalization, which is and to be specific, layer normalization, and the residual connection, which is shown here with this arrow, right? That takes the that's basically a skip connection after that bypasses the self-attention layer. And in addition to these two components, we also have a feed-forward network, and I won't be going into the details of this because this is just plain vanilla, fully connected neural network. So we don't need to discuss the details of this. Next is normalization, which is the same as the normalization we did here, with some minor differences, which I'll discuss later on. And then we have a residual connection. So once the input passes through the transformer block, eventually we have a linear layer combined with a softmax layer, and this gives us different probabilities for different words. Okay, so we eventually will have a probability distribution over different words, and we will sample from this distribution to predict the next word. Now the transformer block itself is repeated multiple times. So this video is concerned with basically wrapping up our discussion around the transformer block, and in the next video I will be discussing how to use the output from these transformer blocks, convert them into probabilities, and sample the next word. So let's get started with the normalization layer. So to discuss normalization, we'll go back to a feed-forward neural network. So what we have here is some input X, which is one-dimensional, okay, and the input passes through 2 hidden layers. And then we have the output, which is also one-dimensional here for simplicity. You can extend this also to multi-dimensional inputs and outputs. So let's say you train this model on by sampling the input X from some training distribution, which is shown here in red. So you collected these samples, you did your stochastic gradient descent using these samples, and then you have some weights for the neural network that help you compute the output with reasonable accuracy. And then you take this model and you deploy it. Okay, so as soon as you deploy the model, you realize that the testing distribution is totally different. So the testing distribution is very different from the training one, and this is what is shown by the purple curve. As you can see, the mean is shifted, the variance is different. So as soon as the testing distribution changes, your model will not behave the same as it did during training. So usually the performance of the model would go down substantially, and you might realize that, you know, in case of training you had an accuracy of 98%. This is just an example. And then during testing, because the distribution shift happens, the accuracy drops to 90%. Okay, so what we conclude from this discussion is that distribution shifts, they make learning very difficult. So if you have distribution shifts, your algorithm won't be able to pick up the intrinsic relationships between the different feature components and give you a reasonable output. So to handle the distribution shift with regards to the input X, it's recommended that you collect samples which are representative of the testing distribution. You combine those testing samples with simulated samples and so on. So the problem with having a distribution shift in the input can be easily managed by having a reasonable training data set. But what we will observe in the next slide is that these distribution shifts also happen internally within the model, and this makes it difficult to learn deeper networks. And normalization, as we will discuss later on, is a way to control these internal distribution shifts. So we can decompose the network into 2 parts. One is shown on the left. So that contains one hidden layer. We denote the weights of this hidden layer by W1. And then on the right, we have shown the second hidden layer, which has the weights W2. Now, now if I hide the network on the left, right, then you can view the right hand side of our network as a model in itself, and that receives as input the output from the left hand side. So let's represent this output as H1. So and this H1 obviously is a function of the weights that we have computed. So when the weights change, the input coming from the left that goes into the right hand side changes. Okay, and this is the key observation, that the input which the second layer is taking in from the previous layer, right, this changes as the weights change. And as you know, the weights change with every iteration of your stochastic gradient. That's why if you were to plot the distribution of this input H1, similar to what we did for the input X, you would observe something like this. So in the first epoch, your distribution might look like the red curve. In the second epoch, it might shift. In the third epoch, it might shift even further. This is just an example to elaborate what might happen. So one thing to note is that we are now treating H1 as our input. Okay, earlier we had the input X and we were studying its distribution. Now we are studying the distribution of H1 because that's the input to this second hidden layer. Okay, now because this distribution is moving around, this makes it very difficult for the right hand side of our model to perform any learning, right? Because this right hand side, this sub model that we have here on the right, this is experiencing internal distribution shift. But this internal distribution shift makes it difficult for us to really squeeze out all the benefits from our learning algorithm, and makes it harder to learn. So that's what we would be handling with the help of normalization. So let's see how the normalization now progresses. Before that, let's have the following notation. So H1, which is the input coming from the left, will have two components. If you remember from the discussion here, H1 is the output of the left hand side, and because we only have two neurons, we will only have a two-dimensional output from the left. So H1 contains two entries. Let's call them H1 and H2. And if we were to plot the distribution of H1, the distribution might fly around or might change as we continue with our learning iterations. So what we do is we perform normalization. So we compute the mean, that's denoted by M1, and we compute the standard deviation of this vector. Let's denote it by S1. We can subtract the mean and divide by the standard deviation. So once we subtract the mean, that means we have centered everything around 0. And when we normalize by the standard deviation, that means we are restricting the standard deviation to 1. So this NH1, which is the normalized H1, would have distributions which would look something like this. Right? So in the first iteration, in the first epoch, you might have a distribution which is shown here by the red, and then in the second epoch, you will have a distribution which is also centered around 0, because you subtracted the mean, and has a variance which is reasonably behaved. So what we have done by normalizing in this way is that we have brought the different distributions together, right? So we have restricted the movement of these different distributions that we have, and now they can't really fly around and cause much of a distribution shift. So once we have done this, we will now let the model choose the mean and the variance itself. So that's the final step. You add trainable parameters y and g, and so these parameters then give freedom to the model to choose the mean and the variance accordingly. And what we have done from our side is to give nh as the input. Okay, and when we give nh as the input, the distribution shift is avoided. So these trainable parameters are learned like every other parameter in the model. It's learned using gradient descent, and this whole formulation here could be easily combined with any standard learning technique. So that's normalization. So next I will very quickly summarize this normalization process for the transformer architecture, the formulation remains exactly the same. It's just that we apply this formulation to each word separately. So what the input was cat is an, we applied self-attention to it, and then we have the output h. We're using this notation to maintain consistency with what we discussed in the past. And this output h, as I discussed in the previous video, can be decomposed into three vectors. So h cat would be a vector that corresponds to the word cat, h is for the word is, and so on. So each of these vectors are d-dimensional, where d is the dimension of the embedding space. Okay, and the key point to remember now is that normalization is performed for each of these different vectors separately. So you would perform normalization for the word cat by subtracting the mean and the standard deviation, and then, as we discussed, we would like to add trainable parameters y cat and g cat in this case, and these parameters then let the model choose an appropriate mean and variance by itself. So we repeat this whole process for each word separately, and finally we get the normalized vector, which is nothing but the different normalized vectors corresponding to different words stacked on top of each other. So it's basically the same as a feed forward network, just that you have to perform this operation separately for each word. And this is where the key distinction between layer normalization and batch normalization lies. So I won't be going into the details of batch normalization, but if you're more interested in this topic, you can read the layer normalization, which I have in the description of this video. I'll talk about residual connections, and we'll be going back to a feed forward neural network because of its simplicity. So we have, let's take the the model that we previously had. So this is model 1 with 2 hidden layers, and let's add a new layer to it. So we take the same model and we add an additional layer, which is shown here in green. Let's denote with h the input or the output coming from the left hand side of the model. So this h would be the same as the output from this left hand side part of model 1. Okay, and then the additional layer is represented with f, and this additional layer then operates on this input coming from the left. This leads us to the output fh, which is then used to compute the output. So we make the following observations, right? One is really straightforward. So model 2, which is shown here on the right, has more parameters than model 1. So when you have more parameters, you have a more complex model. And another thing is, if this additional layer fh, if it does not change h in any way, meaning that if f is an identity operator, right, then we would recover the same output as model 1. That means model 1 would perform the same as model 2 if this additional layer is just the identity operator. Right, so given these two facts, this makes us believe, or at least hypothesize, that model 2 would perform better than model 1. Right? Or at least it would perform as good as model 1. So we would want our learning algorithm to be able to discover the identity mapping, in which case we'll have the same performance as model 1. And in other cases, we should be able to add perturbations to this identity mapping such that model 2 performs better than model 1. Okay, so this would be our expectation. But this is not something that we observe in practice. So if we were to compute the testing error for these two different models, so testing error is shown here along the y-axis, and on the x-axis we have the number of epochs. Then we realize that actually model 2 performs worse than model 1. So model 2 has a higher error than model 1 for all epochs, and this has been observed for practical test cases, and I will recall one of these results in the next slide. But this is the general behavior when you were to plot the error rates. Now you might think, okay, model 2 is more complex than model 1, and that's why the testing error is higher, because model 2 is overfitting, right? And that's not the case either. So if you were to now plot the training error for the two models, the training error for model 2 would be higher than the training error for model 1. And this is quite concerning, because we have added complexity to model 1. and this has resulted in Model 2. So Model 2 has more parameters. So that means training Model 2 is more expensive. Doing inference with Model 2 is more expensive, but we're not gaining anything from this additional expense. So what the authors of these of the paper that first proposes residual connections, and this paper is linked in the description. So they hypothesize that probably, discovering this relation, or the identity operator for the learning algorithm, is very hard. It's difficult for the model to even maintain the accuracy of Model 1, and that's why they proposed residual connections. This is how it looks like. So that's the observation we made. It's difficult to find perturbations to the identity mapping. It's difficult to even discover the identity mapping during learning. But that's why authors introduce residual connections. So in case of residual connections, what you have is first the input coming from the left, which we denote with H, and this input then goes through the additional layer FH. This is the same as before, but in addition to this flow of information, we also have a skip connection. So the skip connection now basically takes H and skips the entire additional layer and pushes it forward to post additional layer operation. And once you have H coming from this skip connection and the FH coming from the additional layer, you add the two, and that's your output. So what we can conclude here is the following. So let's say the true function. So if we would have known the output function exactly, which we obviously don't, then we could have constructed the true function T of H, right? So instead of F of H, if we would have applied T of H, we would have gotten the exact output, but obviously we don't know the output. So we're approximating it, and this approximation is actually H plus F of H. So this means that FH is actually approximating the residual. So that's the key difference between a network based upon residual connection and the plain vanilla network. So the plain network approximates the true function directly. A residual connection based network approximates the residual, as the name suggests. And now if FH were to be set to 0, then you would recover a simpler model. Okay, so if you go back to the slides that we had earlier, so this is Model 1. If we had a skip connection in addition to this additional layer, so if we had a skip connection originating from here to after the additional layer, then by setting the additional layer to 0, we would recover the simpler model 1. And then what the authors realize is basically to learn this null operator. So learning FH equal to 0 is a much more simpler task than learning FH equal to 1 or FH equal to identity. What this means is that during the learning process, we can easily fall back to the null operator, which results in an accuracy which is the same as a smaller model. And in the best case, we can easily add perturbations to this null operator and recover models which perform better than the simpler model. And you can also see this for real test cases. This is the simulation performed by the authors using the CFAR 10 dataset. So you have two models here, one containing 18 layers and the other one containing 34 layers. And the authors are comparing the validation and training errors between these two models, and you can see that the 34 layer model consistently outperforms the 18 layer model irrespective of which iteration you're at. And so this is a result of adding this residual connection, and you would not find the same effect without the residual connection. So in the same paper, authors discuss that if you were to perform this computation without a skip connection or without a residual connection, actually these plots, they flip. So the 34 layer model actually would perform worse than the 18 layer one. So here is a summary of residual connections. So using residual connections, one can take simpler models and improve their accuracy by adding additional layers. So let's put this all together for our transformer block and see how the output looks like. So our input is Cartesian. We perform tokenization, embeddings, and added positional encodings, and then we receive an output X. So this output X again is a stacking of 3 vectors. One corresponds to cat, one corresponds to is, and the last one corresponds to an. Now this matrix X is sent to the self-attention layer, which we are denoting here with f of x to maintain consistency with the previous slides. And in addition to this, we also have a skip connection. Now, this is the residual connection that we talked about. So basically, this is helping us to train deeper networks. We add the two results and we pass them into normalization. So what normalization is doing is trying to control internal data shift. And this internal data shift is what helps us to train models faster and train deeper networks. Okay, so normalization would subtract the mean, would scale by the variance, add additional parameters that let the model choose the mean and the variance by itself. And then finally we have the output where again we have three different rows for the three different words stacked on top of each other. Now this output from the normalization layer then goes into the feed-forward network along with the skip connection. We add the two results, pass them into normalization again, and finally we have the output T of X, which is the output from one transformer block. One thing that's crucial is that this normalization layer and this one, they perform the same operation, but the training parameters that they have, the training parameters that allow the model to learn the mean and the variance by itself, these parameters are different for these two layers. So they don't have any parameter sharing among them. And lastly, as we discussed earlier, this whole transformer block, this is repeated nx times. So what you do is you take this tx and you plug this back in to this entire process, and you repeat this entire process then nx number of times. So this is what is shown here. Okay, so this whole process is repeated several times, and this completes the computation of the transformer block. One crucial thing to note is that the dimension of the output resulting from each of these layers is always 3 cross t. So 3 is the number of words we had in the input sequence, and d is the dimension of the embedding space. So all of these matrices, x plus f of x, this is 3 cross t, same with HO, same after feed forward. So this dimension d is the internal dimension of the model, and this shows up everywhere. And 3 is just the sequence length. So if the sequence was 5, if we had 2 more words added to the sequence, then all the matrices would be 5 cross t. And this is crucial because in my next video, when I discuss how the output is sampled, we would need linear layers to really alter these dimensions appropriately. So these are the key fundamentals about normalization and residual networks. And in the next video, we will then complete the whole transformer architecture by discussing the output and the different sampling procedures.